Hello everyone. Before getting into the meat of today's topic, let's actually recap on something that we learned a long time ago. Suppose say I have this equation, 5x plus 2 equals 7. Now that gives me, let's see, subtract 2, so you get 5. Divide by 5, you get x equals 1, right? So you have a solution, x equals 1. All right, let's do another one. Let's do another one. uh Suppose say x squared. Now you have a quadratic, your highest order of power is 2. So x squared minus 3x plus 2 equals 0, and that gives you x equals 1, okay, or x equals 2. So what do you see here now? These equations, you could call them algebraic equations or polynomials. Okay, basically what's happening is, so you have a variable, and it's you could have different powers of that variable, and what you get at the end, okay, after you solve this equation, after you solve it, you get a number or set of numbers, basically, right? So that's the gist of algebraic equations. So let me write that down. So algebraic equations. So algebraic equations. Uh, so these you have what? A variable. Okay, so you have a variable, and so if you have an equation, involving that variable and its various powers, maybe. So let's see, you have an equation. Okay, you have an equation, and most importantly, when you solve it, okay, after you solve the equation, okay, after you solve it, what you get is a number, or a set of numbers, right? So you get numbers, right? So you get numbers, all right. So how are differential equations, okay, the thing I wrote at the top, how are they different? Well, there's quite a lot of similarity there. Okay, there's quite a lot of similarity there. But to explain that, let's just see one simple example. So suppose say I have dy by dx, some function of x, y is some function of x, and so what I'm saying is the derivative of that function is equal to 5. Now what's happening here, okay, so you have the derivative of some function, right, and you have an equation involving the derivative of a function. Now this is precisely what a differential equation is. Okay, so this is a differential equation. This is a differential equation. And in general, what would be the general definition of differential equations? Like this, you might think, there's just dy by dx, and there could be quite a lot of variation in algebraic equations or polynomials. Like you could have the quadratic x squared, you could have x cubed, x to 5. Same thing here actually. You can have, in similar way, you can have higher power, higher derivatives of y. Okay, you can have higher derivatives of your function. So any equation, okay, any equation that involves the various derivatives, okay, involves the derivatives of a function, okay, involves the derivatives, okay, of a function, that's basically a differential equation. Okay, that's basically a differential equation. Now let's actually try to find some sort of solution for this. Okay, so let's just go by our intuition for now. So this is dy by dx equals 5. Off the top of my head, what I can think of is, okay, so something very familiar to us is, if we differentiate something x, okay, some constant to x, you will get some constant, that same constant right here. Well, what if I put 5 here? I should get 5 here too, right? So uh, the derivative of 5x equals 5. So probably have seen this a million times already. So let's pattern match. So if we say that dy by dx, okay, dy by dx, and this is just another way of writing it is, so dy by dx is the same as 5, but we also said that 5 is the same as derivative with respect to x of 5x, okay? So this has to be the same as derivative of in respect to x of 5x. Now if I just pattern match and make the two things inside the brackets equivalent, what do I get? So if y has to be the same as 5x, okay, that kind of makes sense. So if y has to be the same as 5x, so y would be equal to 5x, right? Y would be equal to 5x. Well, we have a solution for our differential equation. We have a solution for this differential equation. Okay, so that's pretty neat. But what's the most interesting thing? What I find the most interesting thing here is that look at its solution. Look at its solution. It's not a number. It's not a number, unlike what we got, with algebraic equation, polynomials. This is a function, right? This is a function. So, and it should make some sense because of what I said a while ago. Because a differential equation it does basically involve the derivatives of a certain function. Okay, and if you solve that, you should be getting that certain function. Okay, that certain hidden function back, right? That does make sense. So that is these are really the core features of a differential equation. Okay, pretty similar to algebraic equations, but just they're analogous but just slightly different. So let's write all that we have learned so far down. So we have differential equations. So we have our new types of equations. So different shield. Okay, I don't know why I had a brain freeze at that moment. So we have differential equations. Now, what you're gonna have are not variables. Well, obviously you need variables, but the main thing is you're gonna have the derivatives of a certain function. This equation is gonna involve the derivatives of a certain function. Okay, and well, basically, as I said, it's an equation, right? It's an equation, as by going by the name. So you have an equation. You have an equation. Okay, and if you solve it, but the most important thing is you get a function. Okay, you get a function as your answer. You get a function as your solution. Let's see. You get a function. You get a function. All right. So with all that said and done, some of you might have noticed that I did skirt past a certain issue, especially if you love integrals or not. So the thing is, I did say that the derivative of 5x is equal to 5. That's not wrong. That's not wrong. Let's just look at this. Let's just look at this again, okay, and take some more time. So derivative of 5x, okay, equals 5. That is true. That is true. But what happens if I add suppose say 1? If I just add 1 here, well, nothing, right? Because the derivative of 1, you can separate these and take the derivative, and the derivative of 1 is basically 0, right? So it doesn't change this. Okay, so this is still true. Okay, you still have the derivative being equal to 5, and you could basically do the same thing here. Okay, and by the same argument we just made a while ago, y could, it's just as valid to say that y could even be 5x plus 1, 5x plus 1, right? So but if that is valid, if that argument is valid, then why not plus 2 minus 100 plus 9999? Why not all of those constants? So I think you see where this is going. Okay, you can actually add any constant, okay, any constant here, and this would still be valid. I'm going by all the logic I did here. So you could have a plus c here, make them equivalent, and what do at the end what you get what you get is y must be equal to 5x plus c. Okay, and we could have gotten this a bit more simply without that much thinking, if we just use the indefinite integral. So what we had, I'll just take a short moment for this. So what we had is dy by dx equals 5, right? So what's the opposite of differentiation? It's obviously the indefinite integral, right? So if you take the indefinite integral of both sides, this becomes y, the left side becomes y. The right side, you have the indefinite integral of 5 with respect to x. That becomes 5x plus some arbitrary constant, right? So we very easily got what we got right there. Okay, we got right there. What's the important thing here is this solution, what we obtained right here. We didn't skirt past any issue. We didn't neglect anything. We got as comprehensive and complete of a solution as possible. That is why this solution, okay, this solution which encompasses any possible solutions to our differential equation. Okay, encompasses any and all possible solutions to our given differential equation. This type of solution is called the general solution. Okay, this type of solution is called a general solution. So let me write that down. So general solution, and what it basically is it encompasses all solutions. Okay, it encompasses all solutions to my differential equation, to my given differential equations. So I'll write that in caps. So all solutions, it encompasses all solutions. It's pretty neat, pretty neat. Now let's actually try to graph this solution, and that there's some problem in saying that, because I think you can already see this is y equals 5x plus c. C is any constant, right? At the very least any real number. We are taking the real numbers right now. If that is the case, we are gonna have, this is basically a line with slope of 5x and intercept of c. We're gonna have an infinite number of them. There's no end to it, right? There's no end to it. So what I'm gonna do is, just for now, I'm gonna plot a limited number of them. As I've said, this is a general solution, and in general solutions, they do include an infinite number of solutions. That's what usually happens. So yeah, let's actually graph some of these. Okay, so let's say let me just make y, c equal to 5. Okay, so taking our y-intercept as 5. Suppose say then I have some line like this. Okay, so this is gonna be, let's see, y equals 5x plus 5. Let's do another one. Let's say in red. Okay, let's say let's make c equal to, and what I'll have here is something like this. So y equals 5x plus 2. Y equals 5x plus 2. Right? So this is for c equals 5. This is for c equals 2. These are both valid solutions. What I got from a general solution. Let's just do one last one. So let's see something like this. So if c equals, suppose say minus 3, I can say that this is y equals 5x minus 3. So all of these, I just derived them from the general solution. I just plugged in some numbers for c, and I got these solutions. There are actually an infinite number of these lines. Okay, all of them being parallel to each other. So all of these are solutions. And what I'm trying to say is, if you just pick out one solution, if I just wanted, if I just wanted to pick out a certain solution, a specific solution, and what I like about this, topic is the names are pretty obvious. The naming sense is pretty good. So a particular specific solution is actually just called that. It's particular solution. If I just pick out one of them, it's called a particular solution. It's called a particular solution. All right. If that's the case, you might ask, okay, so then I had my differential equation before. Okay, I had, let me rewrite that. So I had this equation before. Dy by dx equals 5. What I got from here is this general solution, y equals 5x plus c. Now, can I get any particular solution from this? Just one solution. Well, no. There's really nothing to move this forward anymore. We cannot just make C into something. If you just wish it to. This is where the line ends. Okay, given the information that we have on hand. But if we are given some more info, then we might be able to do something. So let me tell you. Okay, let me tell you that along with satisfying this, your solution also has to satisfy this one more condition. Okay, that at x equals 1, y needs to be equal to 2. So if I tell you that, let's just plug these numbers right in. So when x equals 1, I have 5 multiplied by 1. We have a plus c. This is all on the right hand side. On the left hand side, you have 2, right? You have 2. So if you solve for this, if you solve for c is no longer arbitrary. It has a certain value that is equal to 2 minus 5. That's minus 3, right? So voila, we have found a certain value for c. If you plug this in our general solution, we're gonna get one particular solution, right? We're gonna get one particular solution, y equals 5x minus 3. And I purposefully made this the same as this. So what I'm saying is, what really allowed us to get to this solution, to get to this particular solution. This is a particular solution. Well, this condition right here, right? This condition right here, the and so conditions like these which allow you to find particular, or another name for these which people like a lot is our actual solution. That's also pretty intuitive. So some the some information, it's mostly numeric, which allows you to get to your particular actual solution. These conditions, okay, these conditions are called initial conditions. These conditions are called initial conditions, okay. And the reason I say in conditions, okay, it's plural because sometimes you need more than one, and when basically higher derivatives, higher orders of derivatives, you need more than one. You need more than one uh, initial condition to solve for the function. But anyways, we'll get into that later. So yeah, I think that should make initial conditions pretty clear. They allow you to go from your general solution. Okay, so they allow you to go from your general solution to your particular or actual solution. Okay, so to your particular or actual solution. All right. So with that all said and done, let's actually just do a problem. Okay, let's look at a problem to just summarize everything that you have done so far. It's going to be a different, slightly different problem. But anyways, so what I'm the problem is the derivative of y with respect to x. You can write it as dy by dx, but another way to write is y prime. Okay, shouldn't forget that. So y prime is equal to 2x minus 1 by x. Okay, so this is my equation, and this is a differential equation, right? This is a differential equation, right? Because it involves the derivative. It involves the derivative of y, right? Obviously you have another independent variable x, and here it was not it wasn't explicit in the equation. But anyways, the main thing is you have the derivative of a certain function, okay, and you have an equation involving that. So this is certainly a differential equation. Let's try to solve this. And as I said, the easiest way to do this, for now, is just to take the antiderivative. So if I take the antiderivative of both sides, on the left I just get y, okay. On the right I get, so if I take the antiderivative of this side, okay, the indefinite integral, anyway, I'd like to spin it, so you get this thing, which is equal to, so x squared, okay, raised to the power divided by 2 minus, okay, so 1 by x, if you integrate that, you get natural log of absolute value of x, right? And so this is not enough. You're taking an indefinite integral, so you have an arbitrary constant. Now this is your solution, right? This is your solution. This is actually the general solution, right? We This encompasses any possible solution to the equation. We didn't use any initial conditions. So this is your general solution. So this is whoops. So this is your general solution. So this is your general solution. That's all fine and good. Now, let me tack on a condition here. Let me tack on an initial condition here. So, let's say that along with this, you also need to satisfy this. When x equals 0, y needs to be equal to 1. Now, this is, as I said, this is an initial condition, right? It's some extra info given to you so that you can find a particular or actual solution. So, this is, let's say, this is your initial condition. Now, if we use this in our general solution, what do we get? Now, let's just substitute the numbers in. What we get is, on the right hand side, we get, x is equal to 1. So, 1 squared uh, minus natural log of 1, okay, natural log of 1 is 0, plus c. This is what you get on the right hand side. On the left, what you get is, y is 0 when x equals 1. So you get 0 here. This gives you a particular value of c, which is c equals -1. Now, if I just substitute this in our general solution, I should get my particular solution, right? I should get a particular solution, which should be y equals x squared minus natural log of absolute value of x. That didn't look that well. Sorry, not plus, minus 1. Now, this is what we call a particular solution, right? So just one particular solution of our given differential equation. And we got this because we had an initial condition and we needed to satisfy that. Okay. So this is a particular solution. Oops, this is a all right. So I think that's enough for this video. We'll continue with this basics basics of differential equations in the next video. So with that said and done, if you appreciated and found this video helpful, please do leave a like, please subscribe, and also yeah, keep supporting the channel and study smart.